right, so this is a problem from the end of chapter 24 on the double slit experiment. So here's the setup. We have two slits that are separated. There are the two slits. And they give us the distance of separation to be, so D is 0.25 millimeters, which is 0.00025 meters. And the distance from the slits to the screen is L. That's 1.2 meters. That's here. Now here's our center line between the two slits like this. And then we get this pattern. So you get a bright in the middle, that's the biggest one. And then you get these smaller bright ones that kind of taper off like this. So this is showing the intensity. The bigger the hump, the brighter it is. So like that, on both sides like that. Okay, so we got bright, dark, bright, dark, bright. And then as far as the fringe order goes, you call this center guy, this is the 0th order bright, this is the 0th order dark, this is first order bright, first order dark, first order bright, like that. Okay? And then the same pattern goes this way, only you'd call those negative. All right, what else? Oh, we got the wavelength of light. So we have these light ray, it's monochromatic light in this problem. So these are rays, but you could show wave fronts like this. Right? The wave fronts would be perpendicular to, there's two ways to show light. Like when we did ray diagrams, you drew it as a ray like this, but then you could also show these as wave fronts where these are, peak, trough, peak, like that, the wave coming in. But anyway, the wavelength of this incoming light is 546.1 nanometers, which I'm going to put that into meters, 5.461 times 10 to the negative 7 meter. So this is the setup. Now, first question. The interference pattern is observed on the screen. Bright, dark, bright, dark, bright, dark. 1.2 meters. Calculate the distance from the central maximum. So here's the central maximum to the first bright region on either side. So let's just go to this guy right here. So here's the first bright region. So what it wants us to figure out is this distance right here. What is that distance there, which we're going to call y? Now, the equations that work, or the equations that apply here, so we're going to that point on the screen, that point on the screen. In order for that to be constructive, so the bottom ray is traveling a farther distance. Now this farther distance works out to be d sine theta, which you also saw in the diffraction grating. The extra distance traveled being d sine theta, where d is this hypotenuse. This makes a right angle right there. And then theta is here. That angle in there is theta. But then theta is also the angle here. It's the angle from the center line between the slits. So theta is in two spots. That's theta, and then that's theta. So our extra distance traveled is d sine theta. For this to be a bright spot, what does the extra distance traveled have to be? M lambda, where that's the wavelength. Because then this ray and this ray will be perfectly in phase with each other. Now, what's m for right here? That's 1. That's where the path difference is exactly 1 wavelength. So, can we solve for y yet? Not yet. So what we're going to do here is make the small angle approximation. So if theta is small, if theta is a small angle, which it is, if it's less than 10 degrees, I should say, if theta is less than 10 degrees, what we can say is this. Sine theta, so look at this triangle here that I'm shading in. Looking at this triangle right in here, sine is opposite, which is what? Y. That's opposite. And then for the hypotenuse, we're just going to say the hypotenuse is L. Okay? We've talked about that in here, right? I think more than once. So sine theta equals y over L. So you take this, plug it in here into that equation, and then you get this equation of y equals lambda L over d times m. Now what if we were focusing on a dark spot? If we would have been focusing on this dark spot here, then how would we modify this equation? It would be what? M plus 1/2. And then same thing for this extra path difference, right? If it's a dark spot, if you're focusing on a dark spot, the equation for the extra distance traveled becomes d sine theta m plus 1/2. But we're not focusing on a dark spot, we're focusing on a bright spot right now. So here's our equation. So to find out this value y, we plug in. So just make sure the units are all the same. So the wavelength is 5.461 times 10 to the negative 7. L is 1.2 meters. Our m is 1 because they told us the first bright spot. And then d is 0.00025. And this comes out as y equals 0.0026, which is the same thing as 2.6 millimeters. So that is the answer for the first bright. Yo.
What if we just found, oh wait, no, I was thinking about like, what if you just found the hypotenuse? Then you need y to begin with, right? So we're just.
Well, look, there are problems that I've come across where you don't want to make the small angle, you don't want to use this small angle approximation. What you would do is you could just literally say tangent theta equals y over L. That'd be the better bet. It takes a little more time, but what you would do is solve this for theta, figure out what theta is, and then plug that back in over here.
Oh, yeah.
Right? You could just do it that way. If the angle's larger than 10 degrees. The two homework problems that I texted you guys with, so was it 39 and 41? They were diffraction grading problems. The angle was like 30 degrees. So in those homework problems from the textbook, you could not make this approximation. You had to use this. Okay? Okay, so part B, so find the distance between the first and second dark bands. So that is like this. So put our pattern back in. So boom, like this. So we're looking for the distance from here to there. Now the spacings are all the same, right? Like this distance here is the same as that distance there, which should be the same as that distance there, right? So if we know the distance, what did we calculate? Hold on. We calculated in the previous question, we calculated this distance from the center line up to here, which was 2.6 millimeters. So now what they want is the distance from here to where? Wait, from the, what did they say? Between the first and the second dark band. So there to there. So, dude, is it true that these spacings are all the same?
Yeah.
So that right there, is that going to be the same as that distance there?
Yes.
Yeah. So it works out. Now if you wanted to prove that, you would just go like this. Just go y equals lambda L over d, and you're going to go m plus 1/2, so you're just going to do the calculation. So if you wanted to find out where this guy was right here, that first dark one, so what's your m there? 0. You go 0, and then calculate this distance right there, right? Calculate that. Then go to this guy right here, calculate where he's going to be, right? Calculate that distance, so what's the m up there going to be? So right here is m equals 0 for dark. Up here is going to be m equals 1. So just change this to m equals 1. You recalculate. In fact, I have these two numbers. This one right here, this distance right here comes out as 0.00393. This is 0.00393 when you calculate it. And then this guy right here comes out as 0.00131. So what's the distance going to be in here? Just subtract these two values and you get this distance to be y equals 0.0026 meters, which is 2.6 millimeters.